What we're going to talk about today is just drainage shape classification in the Pamplona Zone. Broadly speaking, glacial and sedimentation patterns are spatially related. Where are we in the world? We're in Southeast Alaska, where the Pacific plate is being subducted underneath the North American plate, but we have this little Yakutat microplate sort of wedged in between those two. On top of that, we have two sediment wedges, the Pamplona Zone and the Yakataga Fold and Thrust Belt. The Yakataga Fold Thrust Belt is onshore, and the Pamplona Zone, where we're going to be focusing for my talk, is offshore. We generated some testable predictions here that near and within ice sheets, we expect more U-shaped profiles, and away from ice sheets, we expect more V-shaped profiles. We have here the BG and MG, that's Bering Glacier and Malaspina Glacier. These are sort of remnant glaciers from previous ice sheets. What we're doing here is we're trying to quantify spatial relationship between gully profile shapes and these ice sheet extents. Previous researchers have looked at this just in terms of one cross-section across the middle slope. This was one of our collaborators that's working on our new project. He measured the UV shape index, which is essentially finding the power of this function according to a best fit. If you have a power of 1, what we're looking at is a really V-shaped profile, whereas, for example, a power of 2 would be very U-shaped. So 1.5 is the cutoff between U-shaped and V-shaped, but it's somewhat qualitative as well. Swartz's research looked like this. He was able to use his results to identify zones of slope progradation and where we're experiencing sediment bypass. But what we're going to do is compare it to a lot of different things, and we're going to try to be a little more spatial than just doing one profile. We want to interpolate across the entire area. What we're going to focus on for the lightning talk, just for limited time, is the relationship between ice sheet extents and the shape index, although we've compared more variables. It was kind of hard to find a data set. There are many different data sets available for bathymetry here. We ultimately decided to use the smooth sheet bathymetry available here. For example, even with the best multi-beam data available, you can see striping. And even in the acoustic backscatter, you see the same striping just between scans of the same survey. This is the data set we ultimately selected by Zimmerman and Prescott, released in 2015. I ran edge detection on this data set. It looked pretty smooth, but we still identify the same features in the scans. And so this was a compilation of single beam, multi-beam, everything they could find, and regridded to 100-meter cell size. Wanted to build a drainage network here for both ridges and gullies. So I did that in Modelbuilder. Essentially, we're loading the data, clipping the data, inverting and filling the DEM, the typical things you do. I did this for several different flow accumulation thresholds using the iterators within Modelbuilder. And then we'll take a look at that, and then we also will apply some filters, which you'll see why. How do you set up the iterator? It basically works like this. You feed in some data into one of your tools, you attach the iterator to that, you tell it from what value to what value, and then the tricky part that took me a little bit of the learning curve was you have to put your value in one of your statements for raster calculator in this example, as well as in your file name. That's a way to make sure you get one file per iteration, which was important to me. This is what the results look like for the gullies. You can see there are some problems here. This is before we apply any filtering. We have some long segments which are probably not accurate. This is after we've applied the following filters, which were basically length-based and number of points. The one that really helped us out was the second filter, length less than 4,000 meters and between greater than 100 meters as well. That clipped out a lot of those long, incorrect drainages we saw before. This is for ridges, and then after the filter. We had some issues with the track lines. You could see that based on the edge detection that I showed when I introduced the data set. So we wanted to remove the effects of track lines. So what you see here is before we've applied any filtering, as well as before we've done anything with the track lines. And now we've removed anything within 500 meters. We've removed stuff within 500 meters of the track lines, and we've also applied our length filters to our drainage network. So this is what we're going to use moving forward to extract our profile data, which we've done in Modelbuilder again. So the point here is that it may look somewhat complex if you've never used Modelbuilder before, but it's really pretty simple. So we're taking our stream network, taking a subset of those lines. In this case, we used 500. We add the fields we need, which are the endpoints of this profile. And then we turn those endpoints into a line, and we use the tool to sample a long line. In this case, I did it every 100 meters. And then finally, we remove the effects of the track lines, and we extract our data to a text file. Then we feed that text file back into ArcGIS, and it looks something like this. Here's the distribution of our profiles. You can see that some of the profiles are cut off because they were near a track line. We take all those profiles and we want to see if they are U or V shaped, essentially. So window number 1 here, I wrote this little program that guides you through trimming and extracting the profiles. I took just bulk 5-kilometer long profiles at each point. So we may have captured more or less than we actually wanted to. So that's why we have to trim it. Your job, if you're running this program, is to click on the minimum, the left max, and the right max. And then in window number 2, it'll output the statistics for you. And the bottom axis label here is going to be what your best fit exponent is. It'll look something like this. The red color in the background is all possible shapes that I tested with power of 0 to 1. The green, blue, and magenta are similar possible shapes. Another example, if we zoom in, we see we've treated all the possible shapes pretty fairly. The reds, greens, and blues are all pretty equally represented in the extracted profile points graph here. The results look like this, but we wanted to be a little more spatial, so we interpolated our shape index using geostatistical analysts, specifically the geostatistical wizard, in order to do this. There were some points that we rejected. You can see their distributions here. This was basically if we had less than 2 meters of relief across the entire profile, or if our line was highly asymmetric, or there just weren't enough sample points left. Now that we've interpolated this map, we can really compare it with the previous results. So on top here, you see Swartz's profile through the mid-slope. His colors here are zone A, B, C, D, E, et cetera, et cetera. Where we overlap is basically between zone A and a little bit into zone D. So I've extracted a profile on our map here in order to compare. We're basically hitting the U shape in zone A and B, and then down here, we're not so sure. I think we see a general trend here that we're mostly V-shaped, and I think we reflect that in our study as well. We wanted to look at this with respect to the ice sheet extents, and we see that two lobes of the last glacial maximum seem to split near the Kayak Island zone, and these are more associated with U-shaped profiles. In the eastern area, we see one edge of the last glacial max is subparallel to the change in U and V profile shapes. And near the shallow zone surrounding the Kayak Island zone, we see the change in UV contour subparallel to the max glacial extent. We can look at cross plots of this, and anything on the axis here, 0, is actually within the ice sheet. So what we're seeing on the map here is a distance map from the LGM polygon, last glacial maximum. I've also done this for the max glacial extent, and we see basically the same relationship. We see that inside the ice sheets, we're more U-shaped, and as we move away from the ice sheets, we become more V-shaped. There's also a possible relationship here that we see a clustering of sort of 0.5 values at sort of a greater distance. I want to investigate that a little further. So just in summary here, what I was able to find was we see more U-shapes within the last glacial max and the maximum glacial extent. And as we move away from that, we see more V-shapes. some future work here. I was really concerned with the quality of the drainage network. So instead of just doing number of contributing cells, I'd like to do that, but also incorporate slope and relief into that. Maybe refine the drainage network a little bit. I'd like to focus on a smaller area with better resolution and figure out some way of dealing with those asymmetric profiles. I'd also like to test more relationships throughout the area. Thank you.
Thank you.